Namaskara. In this session, we are going to analyze the merge sort. Analysis of merge sort. We have seen that the complexity function of the merge sort algorithm is given by the recurrence equation T of n is T of floor n by 2 plus T of seal n by 2 plus n minus 1, and this is 0 if n equal to 1, and this equation when n is greater than 1. When n is greater than 1, we have an expression, and when n equal to 1, it is 0. First, I am going to get an estimate. Solving this exactly is a bit complicated. We are going to see the details, the mathematical details related to that. Whenever you find something is very difficult to evaluate exactly, you estimate. If you cannot evaluate, you estimate. Get an upper bound to get an idea how big it is. Therefore, we are going to find an upper bound for T of n. Okay? So, that gives a rough idea about T of n. It is not exact expression. It is a function that acts as an upper bound, and that will give some idea on how big T of n is going to be, right. So, the typical way in which the upper bound is derived is to consider an infinite sequence of values, and it should evaluate to a closed form function for that infinite sequence of values. And if a continuous function values are known for infinitely many values, right, you can use them to determine the value of that function for all values. So, we are going to study first T of n for only powers of 2, right, 2 power 0, 2 power 1, 2 power 2, in general 2 power k. Different recurrence equations will require different infinite sequences be chosen. A convenient infinite series, first we will evaluate T of n only for this infinite sequence of values. Okay? The reason why I have chosen 2 power k is floor n by 2 as well as seal n by 2 when n is 2 power k would be 2 power k minus 1, right. Floor 2 power k by 2 equal to seal 2 power k by 2, and that will be equal to 2 power k minus 1. It is of the same form as 2 power k. Therefore, I will be able to write something like that: T of 2 power k equals T of 2 power k minus 1 plus T of 2 power k minus 1 plus 2 power k minus 1. In other words, what we are going to say is, set n equal to 2 power k, then we get T of 2 power k is 2 times T of 2 power k minus 1 plus 2 power k minus 1, because this is n minus 1 and n is 2 power k. Now, you can see the dependence with respect to k. If you observe, something for k is expressed in terms of something depending on k minus 1. So, we can build a chain of substitution and we can unwind this recursion. So, what is, for example, T of 2 power k minus 1? T of 2 power k minus 1 is 2 times t of 2 power k minus 2 plus 2 power k minus 1 minus 1. Now you can substitute this value here. When you substitute that value, you obtain t of 2 power k is 2 times t of 2 power k minus 2 plus 2 power k minus 1 minus 1 plus 2 power k minus 1. This is nothing but 2 square t of 2 power k minus 2 plus 2 power k minus 2 plus 2 power k minus 1. One more term we will derive, and this is equal to 2 square. What is t of 2 power k minus 2? Substituting k minus 2 for k in the first equation, you get t of 2 power k minus 3 plus 2 power k minus 2 minus 1 plus these two terms. I am not repeating it. This term is here and this term is here. And this is given by 2 power 3 t of 2 power k minus 3 plus 2 square. This is 2 power k minus 2 square plus 2 power k minus 2 plus 2 power k minus 1. So, after going through k steps, you get t of 2 power k. After going through k steps, you see a pattern. So, what is the pattern that you see? If I have 2 power 3 here, I have k minus 3 over here. So, after k steps, I will have 2 power k over here and 2 power k minus k as a term. Then you have 2 power k minus, if you have 3, everything from 2, 1, 0 you have. So, this is going to be 2 power k t of 2 power k minus k plus 2 power k minus 2 power k minus 1 plus 2 power k minus 2 power k minus 2 plus 2 power k minus 2 plus 2 power k minus 1. This is t of 2 power 0, which is equal to t of 1, and that is equal to 0. Therefore, this term vanishes because it is 0. And now, how many terms are here? There are k terms. There are k terms. Each one has got 2 power k. Therefore, that is equal to k times 2 power k minus 1 plus 2 plus 2 square up to 2 power k minus 1. This is equal to k times 2 power k minus, this is a geometric progression. First term is 1, common ratio is 2, therefore, it will be 2 power k minus 1 divided by 2 minus 1. 2 minus 1 is 1, therefore, the denominator can be completely ignored. Hence, I get this is k times 2 power k minus 2 power k plus 1. k times 2 power k minus 2 power k plus 1. This is what I am getting for 2 power k. We express this as a function of n, and when we do that, t of 2 power k is k times 2 power k minus 2 power k plus 1, and that is equal to log n times n minus n plus 1. That is n log n minus n plus 1. T of n, we call that n equal to 2 power k. Therefore, k equal to log n to the base 2. So, that is what I have written here. This k is replaced by log n. 2 power k is replaced by n. 2 power k is n. Therefore, T of n is n log n minus n plus 1 if n equal to 2 power k. So, for n equal to 2 power k, you have a formula. For n equal to 128, it is a power of 2. You have a formula. If n equal to 1024, you can use this formula. However, if n equal to 100, you can't use this formula. This formula is valid only for powers of 2. So, the first question is, how do I extend something that I have derived for special values to all values? Okay? I have a function t of n, its values are available for powers of 2, but I want the description of the function for all n. So, how do we extend something that I have derived for only powers of 2 for all values of n? The claim is T of n is going to have the same order, because we are interested only in upper bound. It will be of same order, provided the function does not have wild behavior. It should not be monotonically increasing and then decreasing or fluctuating. If that is the case, for example, even a linear one, so you could draw the, you observe only on integer values. So, for 1 it is 1, for 2 it is 2, for 3 it is 3, for 4 it is 4. The function value. Okay. This you made an observation only on special values, not for all values of n. So, let us say you have observed that a function f of n equal to k for 2 power k. Other values I do not know. In between it could be anything, right. I have this value, then I have this value, then I have this value. In between, what is the value of that function? I do not have a closed form of f. I can't evaluate that. When it is a power of 2, I have a formula, but when it is not a power of 2, how do I get the bound? In between, the things can become way fluctuating that you may not have even a polynomial time bound. That is the reason why stopping with a conclusion on a function through its values on only specific inputs, here only powers of 2. It requires a mathematical proof. You should not simply assume that this is going to be true for all n. So, what is that we do? Here is a very powerful and nice technique. Prove first that f of n, here t of n is monotonic T of n is monotonic. This is very important. If it is monotonic, then it can't go and then it can't decrease. It can keep on going and it will go somewhat parallel to the guess function that we have. So, if T of n is monotonic, then what we can do is we can use this fact to extend a solution for specific values to all values. Okay. So, and then use monotonicity to extend T of n for all values. Earlier you had T of n only for powers of 2. So, let us first prove the monotonicity. How to prove that T of n plus 1 is greater than or equal to T of n? This is monotonicity. How do we prove this? So, T of n plus 1 is T of T of floor n plus 1 by 2 plus T of seal n plus 1 by 2 plus n plus 1 minus 1. This is the recurrence equation. So, I am going to make a strong induction hypothesis. What is the strong induction? T of n is monotonic up to a particular value, right. That is, for all smaller values, for all 1 less than or equal to k less than or equal to n, T of k is greater than or equal to T of k minus 1. Let us assume that T is monotonic for these values, that is, it is increasing up to some values. We will show that it is increasing for the next value n plus 1 also. This is strong induction hypothesis. All previous values you take something to be true, now you prove that it is true for n plus 1 also. Now, by monotonicity, this is greater than or equal to T of floor n by 2 plus T of seal n by 2 plus n minus 1. This n plus 1 is replaced by n. This has been made smaller. This is also made smaller by induction hypothesis. This is also smaller by induction hypothesis. And now this is T of n. Therefore, I have shown that T is monotonic. T is monotonic for all values of n. How do I prove it? Induction on n. Base case is trivial, n equal to 1. T will have some value, but the complexity, that is 0, right. So, it is monotonic for all values of n. Okay. Now, here is what you are going to do. If n is not a power of 2, if n is not a power of 2, let it sandwich between two consecutive powers of 2. That is, let 2 power k minus 1 less than n less than 2 power k. It is strictly like 100. 100 is in between 64 and 128. 64 is a power of 2. 128 is another power of 2. Between them 100 lies. Every number n will be in between two successive powers of 2. Because powers of 2 is an infinite sequence, it is going to cover all n. So, every n is going to be in between two powers of 2. Let us assume that k is between 2 power k minus 1 and 2 power k. In this case, if you take log, you see that k minus 1 is less than log n is less than k. So, log n is a number which is sandwiched between two successive integers. This means k minus 1 is equal to floor log n and k equal to ceil log n. Because it is in between two integers, strictly between two integers. This is not true when you have one of them as an integer. It is strictly between, therefore, floor is k minus 1 is floor log n and k is ceil log n. Okay. Because of this, 2 power k, see 2 power k minus 1 is less than n. Therefore, 2 power k is less than 2n. Multiply this by 2, you get 2 power k to be less than 2n. Okay? If 2 power k minus 1 is less than n, 2 power k is less than 2n. Now, what we have is the following. Because of this, f of n is less than or equal to f of 2 power k. F of n is less than or equal to f of 2 power k. Why? This is because n is less than 2 power k and f is monotonic, therefore, f of n is less than or equal to. But f of 2k has a formula, k 2 power k minus 2 power k plus 1. This is the formula for. Now, this is less than k 2 power k. Instead of subtracting 2 power k, I will subtract only n minus n. I am subtracting a smaller number, that is why equality has become minus n plus 1. And this is less than 2 power k is less than 2n. Therefore, this is k is a log n times 2n minus n plus 1. Therefore, when 2 power k minus 1 less than n less than 2 power k, t of n is less than t of 2 power k, which is equal to k times 2 power k minus 2 power k plus 1, which is less than k times 2 power k minus n plus 1, which is less than n seal log n minus n plus 1. I have not solved exactly. I have not found the value of T of n exactly for all n. I know value of Tn exactly for all n which are powers of 2. I know that T of n equal to n log n minus n plus 1. This much is true, T of n. This is true when n is a power of 2, but this is what is true. 2 power k is less than 2n. I am sorry, there was a minor 2 power k is less than 2n. 2 power k is less than 2n. So, I have to replace 2 power k by 2n. My apologies, I have to rewrite this. 2 power k. This is less than, k is log n. 2 power k is less than 2n minus n plus 1, and this is nothing but 2 n log n minus n plus 1. It is some value, but it is less than 2 n log n minus n plus 1. T of n equal to n log n minus n plus 1 when n is 2 power k, and this is the expression when n is not equal to 2 power k. When n is not a power of 2, this is the bound that we have. Therefore, we can write T of n is less than or equal to 2 n log n minus n plus 1 for all n. For all n greater than or equal to 0, this is true. This fact is true for some value, this fact is true for some value. Consolidating, it will be less than or equal to 2n. That shows T of n is order n log n. Very important conclusion. T of n is order n log n. What we have done is, we have found exact value, but we used monotonicity. This is the crucial step. N is less than 2 power k, therefore this is, and straightforward algebra after that. Okay. So, now we have some idea that it is of order n log n. Okay. We can now, without worrying about the monotonicity and special value derivation and other things, we can show that T of n is less than or equal to n seal log n for all n. T of n is less than or equal to n seal log n. So, how did I get this guess? I did some computation for special values, then I used some bound. It is roughly coming to n log n kind of an order. So, I will prove this. T of n is less than or equal. This proof is called guess and verify. This is a guess I made. This guess I made based on intuition and experience and other things. Once you made a guess, you try to prove by induction. So, we will see how to prove this bound, as well as we will see the exact way to solve the recurrence equation by working out some beautiful mathematics related to floor and seal functions, and then we will conclude the discussions related to merge sort. I stop at this point. Thank you.